Transverse and longitudinal waves. If we stretch a spring between 2 points, we can produce a wave which travels along the spring. We can oscillate the spring like this, and the wave will travel in this direction. Here, the plane of oscillation or vibration is perpendicular, or at 90 degrees, to the direction of energy transfer. This produces a transverse wave. The prefix trans means across, so the vibrations are across the direction of energy transfer. We can draw the wave like this, and if we mark on the equilibrium, or point of no disturbance, then this arrow gives the amplitude, which is the maximum displacement from equilibrium. Make sure the arrow touches here and here. The wavelength, which is given the Greek letter lambda, is from crest to crest, or from trough to trough, or from any point on the wave to the same point on the adjacent wave. Again, make sure that your arrow clearly goes from one point to the same point. Don't be tempted to do a short arrow just around about that sort of length. So the wavelength is defined as the distance from a point on one wave to the equivalent point on the adjacent wave. Waves on a water surface are transverse, as are all the electromagnetic waves: radio, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. Here we have the spring again. If we now move the spring like this, the energy transfer will again travel in this direction. So now the plane of oscillation or vibration is parallel to the direction of energy transfer. This produces a longitudinal wave. The vibration is along the direction of energy transfer. That produces a wave that looks something like this, where we have compressions, where the coils of the spring are close together, or the air particles with a sound wave. Rarefactions, where the particles are further apart. The wavelength would be, for instance, from a compression to the next compression. The wavelength could also be from rarefaction to rarefaction, or any point to the same point on an adjacent wave. Sound waves are longitudinal. Mechanical waves, such as those on a spring, can be longitudinal or transverse. When a water wave passes, the water molecules themselves don't travel with the wave, they just oscillate about their original position. This is why a ball floating on water bobs up and down as the wave passes. It doesn't follow the wave. When sound waves pass through air, the air molecules don't travel with the wave, they simply oscillate about their original position. When sound passes through a patch of smoke, for instance, the smoke doesn't follow the sound. Frequency. Here we have a wave and an arrow here marking a particular point. Frequency f of a wave is the number of complete waves that pass a point in 1 second. So if this wave moves like this, 5 waves pass the arrow in 1 second, giving a frequency of 5 Hz. The symbol for Hertz is a capital H and a lowercase z. If 5 waves take 1 second, each wave must have taken 1/5 of a second to pass. The time taken for one complete oscillation is called a time period, given the symbol capital T. Time period, then, is 1 over the frequency, or T is 1 over f. So a wave with a frequency of 250 Hz, or 250 complete waves per second, has a time period of 1 over 250 Hz, which gives 0.004 seconds. Frequency is 1 over time period. F is 1 over t. So a wave with a time period of 0.05 seconds has a frequency of 1 over 0.05 seconds, which is 20 Hz.